In Chapter 7, we're going to take a look at atomic structure and atomic behavior. What are the bits and pieces that make up the atom? How do those various particles move inside the atom? And why do they do what they do? You've learned about the atom, you learned about some basic structures, but have you ever stopped to think about something? Electrons move. You've been told that. But you also have learned in the real world when things move, eventually they stop moving thanks to gravity and friction and all that good stuff. Why do the electrons keep moving? Why don't they eventually slow down? And since they're negatively charged, nuclei are positively charged, why don't they just get sucked right into the nucleus? Those electrons, as they move, use up energy. But yet they maintain their distance from the nucleus. They don't just crash right into the nucleus. How come? Well, the primary reason is they absorb energy from the outside. Turns out electromagnetic radiation is the primary outside source. Electromagnetic radiation is the energy that is given off by stars and various other things. Energy in general travels over long distances or short distances in waves. And different forms of electromagnetic radiation have different characteristics. They also have some things that are in common or some similarities as well. All electromagnetic radiation have wavelengths. Symbol for wavelengths is lambda. Looks like an upside down Y. Wavelength units tend to be in nanometers. N is 10 to the negative 9. All electromagnetic radiation also have frequencies. This isn't a V, this is a Greek letter nu. And if you're going to handwrite it, it kind of looks like a swoopy backwards V or a windblown V. The Greek letter is nu. And if you'd rather use F for frequency, that works as well. Units for frequency are hertz. A hertz is 1/2 or inverse seconds. It can be waves per second, cycles per second, rotations per second, but it's 1/2. All electromagnetic radiation also travel at a fairly constant speed. And they travel at a constant speed in a vacuum, and that speed is represented by c. C represents speed of electromagnetic radiation in a vacuum, or in air actually, since air is so low density. And the value for C is 3.0 times 10 to the positive 8th meters per second. You've probably heard of that as the speed of light. Well, light's one form of electromagnetic radiation, but there are a variety of others, and you'll need to figure out more about them as we get there. So, frequency, wavelength, speed are all related to each other in the equation that's shown there. C, or V for velocity, is equal to the frequency of a wave times its wavelength. Okay, here is a picture of the electromagnetic spectrum. As we look at this diagram, on the left-hand side of the diagram, we have very long wavelengths, 10 to the 4th meters. We have very low frequency. We also have low energy on the left. On the right-hand side, we have very high frequency. We have very short wavelength. We also have high energy. As we move up the electromagnetic spectrum, we start out at the low energy end with radio waves and microwaves, TV waves. Radio waves are considered lower. Microwaves are next. Then we get to infrared. Infrared radiation essentially is heat radiation. That's the stuff that's given off by heat lamps, either in buffet tables or if you've got heat lamps in your bathroom. Those are putting out infrared radiation. Visible light is a very, very narrow band of the electromagnetic spectrum, pretty much right in the middle. And the colors go from long wavelengths, red, to short wavelengths, violet. On the higher energy end of visible light is ultraviolet light. Black lights are made of ultraviolet light. Sun kicks out lots of ultraviolet light. That's what gives you suntans and sunburns. Higher energy yet, we get to X-rays. And finally, the most energetic of electromagnetic radiation are gamma rays. They all travel the same way. They all have wavelengths. They all have frequencies. And as they increase in frequency, they increase in energy and their wavelengths get shorter. So what do you need to know? For visible light, you need to know waves. So violet wavelengths are short. It's 400 nanometers. Red wavelengths are the long ones. Those are 700 nanometers. You need to know that range for visible light. You need to know the relative order of energy. So radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. You don't need to know what the cutoffs are, but you do need to know the order in which those occur. Molecules, which is what everything is made of, can convert one form of energy to another lower form of energy. So for example, sunlight's made up of all of these energies, and sunlight that hits your clothing can be converted from high energy to low energy. For example, UV light, when it hits something, the molecules absorb it, but then when they re-emit it, they re-emit it at a lower energy level, sometimes in the visible range. That's why when you shine black light on something, it looks to be a slightly different color many times than when you look at that same thing in regular sunlight or lamplight, because it's taking that ultraviolet light, it's emitting it at a higher energy, and it changes the color. Visible light can be absorbed by things and gets emitted as infrared. Classic example of this, you wear something really dark outside on a hot sunny day. Where it's dark, you get hot. So it's absorbing all those visible light rays. They get emitted as heat, which makes the thing warm up.